Hello and welcome back to another edition of Test Corrections with Mr. Morales. Guaranteed to be highly awkward and extremely informative. All right, here we go. Today we're going to be looking at the Doppler effect. Specifically, we'll focus in on how the Doppler effect affects sound and sound waves. So in the example given on our first quiz, we were told that given a wavefront diagram, so that's the picture given right here. This is a wavefront diagram. We said that this block with the dot in the middle, that is me running through the classroom, screaming at a constant frequency. There are stationary observers, let's say students A, B, C, and D. Which of these students will hear the highest frequency? Okay, well, we want to make a claim based on this question. So we want to be able to say observer blank here's the highest frequency. So far, I'm not sure. So I'd like to look at the reasoning and evidence, and then we'll come back to our claim. Let's take a look at this diagram. Based on what we know, let's try to answer some questions about it. Like, which way is Mr. Morales running? Well, we want to think about the Doppler effect. The Doppler effect says that as an object is moving toward you, the waves of sound are being compressed in front of that moving object. So in this diagram, I am moving toward object B, or observer B. We can tell because the wave fronts in this diagram are more close together than they are in any other direction. Now, because the wave fronts are close together, that tells us that the wavelength is smaller. Each of these wave front lines represents a peak or trough in the wave of sound. So if these waves are closer together here, I am moving in this direction. All right, let's look at our reasoning. We have to go to the equation which says that frequency is equal to the velocity of the sound divided by its wavelength. Well, just focusing on frequency and wavelength, we see that they are inversely proportional, meaning that as one thing goes up, the other one is going to go down. So as these waves get closer together, meaning their wavelength is getting smaller, wavelength is decreasing, that means that the frequency is increasing. So smaller wavelength means a higher frequency. Remember, frequency is like pitch. So to say the frequency is getting higher means that the sound instead of is ah. So we could look at that the other way and say that for maybe observer C, where we have a larger wavelength, that they are perceiving a lower frequency sound. They're hearing, oh. There's some more of that awkwardness, I promised. All right, so now that we have this equation, let's see if we can put that into words. And I've left a few little clues here saying, let's use the terms wavelength, perceived frequency, and Doppler effect in our answer. All right. Well, we could say that observer B, or actually, we don't want to talk about the diagram here. We just want to speak generally about this phenomenon in reasoning. In evidence is where we will cite particulars from this picture. So we want to say that according to this formula, as frequency will increase as wavelength decreases. So let me just put that into a sentence. As wavelength decreases, frequency increases. Now we need to bring the Doppler effect into it. According to the Doppler effect, an observer with a sound moving toward them will hear a higher perceived frequency than one moving away. Now, one thing I left out of this description is velocity. Well, that's because velocity is constant. The speed of sound is not going to change whether the sound source is moving toward, away from the observers. So we can kind of ignore that in this discussion. All right, now, in evidence, let's just point out what we see. Use the terms wavefront and distance. Okay, the distance between wavefronts in the diagram. So this is evidence. So now I'm I am referencing the specific data that is being given to me. The distance between the wavefronts in the diagram is closest near observer B. I should also point out it's not because the sound is closer to observer B or further from observer C. It's the relative movement toward observer B. Being closer or further might affect the volume, but it wouldn't affect the pitch. Okay, so now I have the information that I need to go back to my claim, which is which observer will hear the highest frequency. So I can make a simple claim. Observer B will hear the highest frequency, and therefore observer B here's the highest frequency. And voila. Okay, let's take a look at our bonus question. A little math. Suppose that when Mr. Morales is standing still, he is screaming at a frequency of 3,000 inverse seconds or hertz, cycles per second. The velocity of sound in air is 331 meters per second. What is the wavelength of his scream? Sound waves. Show your work. All right, well, just get out our handy dandy equation. So there are different ways that we can use the equation. Different forms of this equation would be velocity equals frequency times wavelength. We can just manipulate that. I'll write the three different forms. So we've got frequency equals velocity over wavelength, and wavelength equals velocity over frequency. Three ways of saying the same thing. What am I being given in this? I'm being given the frequency. and I'm being given the velocity. So what am I being asked for? I'm being asked for the wavelength. So let me look at for the equation that is going to solve for wavelength, and that's the third one. So wavelength equals velocity over frequency. That's 331 over 3,000. And I can certainly use a calculator to figure things out. And that gives me 0.11. And the unit for that would be meters. Easy. All right. Good luck with the retake. Make sure that you would be comfortable if you saw a diagram like this and it asked you other things like who is hearing the lowest frequency, which direction is the person traveling. We need to be able to interpret this kind of drawing and explain the Doppler effect in doing so. All right, thank you for your time.